Okay. Now we continue with the last talk before the Ramirez de Arellano presentation, the Professor Ramirez de Arellano presentation, and we introduce Professor Tovar, who is one of the organizers of this event, and we thank you very much. And we continue with the talk of Bicomplex, Poisson's problems 1 and 2. Professor Tovar, you can continue.
Ok, muchas gracias. Primero voy a decir algunas cosas relacionadas con Enrique. Bueno, al profesor Ramírez de Arellano, la primera vez que me encontré con él fue en la licenciatura, tomando el curso de variable compleja 1. Ahí fue cuando por primera vez me encontré al profesor Ramírez de Arellano. La introducción la había yo tomado con el doctor Eugenio Filloy. Entonces, pues ahí, a partir de que tomé el curso con el profesor Ramírez de Arellano, pues como decimos aquí en México, pues le cayó el chagüiste, porque de ahí en adelante él fue después mi asesor en la tesis de maestría y luego mi asesor en la tesis de doctorado, ¿sí? Entonces ahí fue donde me encontré con Enrique académicamente, y a partir de eso pues ya comenzó esa vida académica con el profesor Ramírez de Arellano. Más tarde voy a hacer algunas reflexiones y diré algunas anécdotas después de que el profesor Ramírez de Arellano diga algunas palabras. Esta plática que voy a dar, this is a joint work with Lino Reséndiz and Yesenia Bravo. Yes, in similar way to Alberto Borskowski, I will present my talk in Spanglish. I mean, I will give some comments in Spanish and some comments in English. Anyway, my presentation is in English, and then I am willing to receive in any moment any question. Okay? So, consider first the Weierstrass theorem in C. Let B be a domain and delta n a discrete sequence in B, then there exists an analytic function different to the zero function, whose zeros coincide exactly with delta n. As corollary, we can prescribe zeros and poles for meromorphic functions. This is the classical Mittag-Leffler theorem in C. This theorem, as you know, helps us to prescribe poles and principal parts for when you develop the function in Lorentz series. Okay, so what happened if we could generalize these statements? Okay, we return to page 16. Well, so it's impossible. If we want to generalize these statements to several complex variables, we have that it's not possible, because zeros and poles are not isolated points in several complex variables. Zeros and singular parts are subvarieties in several complex variables. So in that sense, it's not possible to generalize these statements to several complex variables. See? But we can give another equivalent statement for both theorems in this way. Consider a domain in C or in C2, well, or in Cn. We will say that this pair, functions and and open defines a cosine 2 family on omega if uj is an open covering of omega and fj is a family of meromorphic functions fg such that fj over fk is an holomorphic nowhere vanishing function on the intersection. Okay, so in this way we can give another similar equivalent statement to Weierstrass theorem. Let B contained in C, a domain, and this part a cosine 2 family on B. Then there exists a meromorphic function in B such that the union results also a cosine 2 family in B. So this statement is equivalent, is not too much complicated, it's equivalent to the previous one, but in this sense, this statement has sense to generalize to several complex variables. So what happened in C, but I will concentrate in C2 because bicomplex numbers are similar to C2 in some sense. Let X in C2 be a domain and consider this pair of cosine 2 family. So it's possible to find a meromorphic function such that this union results also a cosine 2 family. So this is the problem is why problem and not theorem in C2? Because in C, both statements, the previous one and this one, are equivalent. But in C2, results that not always this problem, this statement has a positive answer. Yes, that's the reason why it's a problem. Okay, so is the case we can do the same for the Mittag-Leffler theorem and define a bicomplex a cosine 1 family and to give another equivalent statement for Mittag-Leffler theorem. This statement is equivalent to the first one, and in this way it's possible to consider this statement in several complex variables. Okay, well. Bien, lo que acabo de decir, déjenme explicar algo en español. Estamos hablando de teoremas de prescripción. O sea, con el teorema de Weierstrass uno puede prescribir polos, es decir, en lugar de decir, te doy una función y encuéntrame los ceros, es al revés. Yo doy un conjunto de ceros, a ver, encuéntrame una función que tenga exactamente estos ceros. O en el caso de Mittag-Leffler, en lugar de te doy una función, encuéntrame sus polos, sus partes principales, es al revés. Te doy los puntos, quiero que tenga esas partes principales. ¿Se puede? En una variable es posible. En varias variables, cuando generalizamos, no siempre. ¿Ok? Bueno. Lino Resendiz just presents us the basic rules of bicomplex numbers. Okay, so just then I think it's not necessary to repeat. Just let me tell you, let me give you some comments about it. Okay, so the problem, as you know, in bicomplex number is that we have an addition, we have a multiplication. The multiplication is commutative, but the problem in the case of bicomplex numbers are the zero divisors. And this E and E dagger defines the set of zero divisors. Okay? So, if we combine I, J, and K, we can obtain several representations for Bicomplex numbers. But I will concentrate just in two representations, the normal representations and the idempotent representation. Well, okay. We have also several conjugations instead instead of one complex variables that we have just one. We have several conjugations, but we will concentrate just in the CK. I will concentrate just in some special conjugation, and we have several norms, and we will concentrate just in this norm. Well, we will consider Bicomplex functions, I mean functions defined in the Bicomplex numbers with values in Bicomplex numbers, okay? And by the properties of Bicomplex numbers, we can endow to Bicomplex numbers a topology similar to R4. So we can talk about domains in zero divisors. This is another way to describe the null count. Null count is the set of zero divisors. Zero divisor is given in this way. This is another way to present the zero divisors. Okay, so we are going to consider Bicomplex derivative functions. Let me remark that the definition of the derivative is similar to one complex variable. But we have to be careful with the zero divisor. So we require that zeta minus zeta 0 be an invertible complex, an invertible bicomplex number. Okay. Well, it seems that this definition of derivative could result a little bit weak, in the sense that it's not possible to approximate the point in any direction. But let me tell you that it's not exactly. In one complex variable, this definition is equivalent to the stall conditions. What it says, these stall conditions? Let me tell you this, that f is complex derivative, is complex derivable if f can be expressed in this way. Delta f is equal to a delta zeta plus epsilon delta zeta, where epsilon goes to 0 when delta zeta goes to 0. Well, we have the same situation in Bicomplex number. Yes, this definition is equivalent to this stall condition, but with the advantage that here we have no problem with zero divisors. Okay. Furthermore, we have that what happened when we, this is the XA dagger, this is the XA. What happened when we approximate to this point in this direction? We obtain the directional derivatives in direction E and direction A dagger. So, and this derivative is equal to this derivative, this directional derivative E plus the other directional derivative E dagger. This result will appear in some paper that we hope that appears at the end of this year. Okay? Okay. So, okay. Lina shows, I think, this theorem. Yes, this theorem is very important because give us a formula to the question is, how can I construct a bicomplex holomorphic function? The answer is very easy. Take any pair of analytic functions in C, put it to one in here, and put in the second one here, and you have a bicomplex holomorphic function. This is a very important result that we use in this work. Something that we use very often is the projections of bicomplex numbers in C, okay? And also we use very often this kind of projection, the projection in direction E and the projection in direction E dagger, given in this way. Okay. So, as I told you, F is a bicomplex holomorphic function. If F can be extended as writing in this way, but what happened with the bicomplex holomorphic theory? Bicomplex holomorphic theory results an amphibian between one complex variable or one complex function theory and two complex function theory. Yes, and some results are completely similar to one complex variables, and some others are similar to two complex variables. For instance, what is a remarkable difference between one complex variables, two complex variables, and bicomplex holomorphic functions? In one complex variables, the concept of domain of holomorphy has no sense, because every domain is a domain of holomorphy. But the concept of domain of holomorphy is one of the pillars of the theory in several complex variables. So it's very important. What happened in bicomplex theory? Domains of holomorphy has sense, but every domain of holomorphy results a product domain. And another remarkable difference with those theories is that every holomorphic function can be extended bicomplex holomorphically to the minimum product domain omega hat containing omega. Okay, that is, if you have some function in every domain, this F will produce the completion F hat to the minimum product domain containing omega. That's an important result. The extension F hat is taken on the biggest domain generated by F. This is a consequence of G1 and G2 are defining on the respective projections. What happened with zeros of bicomplex holomorphic functions? I told you that this theory is an amphibian. Well, why? Because zeros can result isolated and can result not non-isolated. This theorem says that if f is a bicomplex holomorphic function not identically zero, then if f takes at least one invertible value, then its zero set is either the empty set or a set of isolated points in omega. If f is concentrated in this way, then its zero set is a countable union of portion of complex lines parallel to the zero divisor line LE dagger. If f of zeta is concentrated in this way, for all zeta, then its zero set is a countable union of portions of complex lines parallel to the zero divisor LE. Okay, in bicomplex theory, you can also express, you can develop the function in Lorentz series. You have also the equivalent to the inner, the limits to the upper and the limits of the ring given in this way. So in bicomplex theory, we say that zeta zero on the boundary of omega is a singular point if there not exists a bicomplex neighborhood P of zeta zero and a bicomplex holomorphic function f hat on the beta zero such that f is equal to f hat on the intersection. This definition is similar to the general definition of singular point in one complex variable. How we can define a bicomplex meromorphic function? It's in a very natural way. F is the quotient of G over H. Yes, the quotient of two bicomplex holomorphic functions, where just we have to be careful with H, that H of zero is not in the new cone. So a function is a bicomplex meromorphic if and only if the function expressed in the idempotent form G and G2 are complex meromorphic functions. Okay. So what happened in general with the singularities in bicomplex theory? We have combined situations. Yes, we have a pair expressed in the idempotent way. We have a combined situation. We can have pairs of normal regular points. We have poles combined with regular points. We have poles with poles. We have essential singularities combined with poles or poles with essential singularities or pair of essential singularities. See? So, okay. This is the definition of pole or a strong pole. There's a pole if this or this tends to infinity, and is strong if in both directions tends to infinity. We have also a bicomplex Great Picard's theorem for the bicomplex case. Given with this combination of situations. Yes, well, I showed you previously this theorem and the corollary. And this is the bicomplex version of Weierstrass theorem. If theta n is a discrete sequence in omega hat is the minimum domain, product domain containing omega. Then there exists a non-trivial bicomplex holomorphic function, f of theta, with domain in omega hat, whose zero set, theta mn, contains the sequence theta n. But if theta n is beta 1n, is a discrete sequence in the projection, then there exists a bicomplex holomorphic function with domain in omega hat, whose zero set coincide exactly with the sequence of portions of complex lines. If theta n is now concentrated in the other direction, then there exists a bicomplex holomorphic function with domain in omega hat, whose zeros coincide exactly with the sequence of portions of complex lines. But if omega is different to the minimal domain containing omega, and beta n is a discrete sequence of points, but not in omega hat, then there is no bicomplex holomorphic functions different to the identical function zero satisfying A, B, and C. Also, in bicomplex theory, we have a fundamental theorem of algebra, but with some exceptions. I will not present this version because it's out of this subject. Well, okay. Well, what happened with the, at the beginning, I talk about the Poisson 2 problem. Well, I show you the definition of Poisson 2 family, okay? What happened in the bicomplex case? We will say that this pair defines a bicomplex Poisson 2 family on omega in bicomplex numbers, if this family is an open covering of omega, and this family is a family of meromorphic functions such that the quotient is a bicomplex meromorphic in the intersection and nowhere vanishing function in both idempotent components. Well, I showed you previously this theorem. This also I showed you this Poisson 2 problem. And this is the Poisson 2 problem, the bicomplex case. If this pair is a bicomplex Poisson 2 family on omega, is there a bicomplex meromorphic function such that this pair results also a Poisson 2 family? This is true. Well, in this in the bicomplex case, the situation is similar to one complex variable. Both statements, the classical and the statement given in terms of families of functions and coverings, results also equivalent. So, if FGUG defines a bicomplex Poisson 2 family, then this is another important situation. If you give any bicomplex Poisson problem in some omega, this family induces a bicomplex Poisson 2 family on the completion, I mean on omega hat in the minimum domain product. So we have this theorem. If Fj and Uj defines a bicomplex Poisson 2 family, then there exists a bicomplex meromorphic function on omega hat such that this result also a Poisson 2 family. I mean the theorem, the Cousin two problem in Bicomplex case has positive answer in this case. What happened with if we have different solutions for a Bicomplex Cousin two theorem? This corollary says that every two solutions differ by a Bicomplex nowhere vanishing holomorphic function, where H is a nowhere vanishing Bicomplex holomorphic function on omega hat. And as I told you, this statement and the previous one are similar. That's the case also with the generalization of Mittag-Leffler, Bicomplex Mittag-Leffler theorem, given in this way, or given in terms of pairs of functions and coverings. Okay. Okay. As I told you, we will say that this pair defines a Bicomplex Cousin one family in omega if uj is an open covering and fj is a family of Bicomplex meromorphic functions, such that this different is a Bicomplex holomorphic function. As you know, the Cousin one problem in several complex variables is well known as the additive Cousin problem, and Cousin two problem in several complex variables is well known as the product Cousin two problem. It's completely similar in the Bicomplex case. So this is the same Mittag-Leffler theorem, but written in terms of pairs of functions and coverings. Let X in C a domain and FG uj a Cousin one family on X, then there exists a meromorphic function such that this union results also a Cousin one family. Okay. Okay. Well, I am writing here what happened in C2. In C2, we have the Cartan theorems results that he says that let X an open set in C2. Then Cousin first problem has solution if X is a domain of holomorphy. Okay. So, Cousin one problem in Bicomplex case, if FG is a Bicomplex Cousin one family, is there a Bicomplex meromorphic function such that this union results a Bicomplex Cousin one family? The answer is positive. This is the theorem. If Fj uj defines a Bicomplex Cousin one family in omega, then Fuj induces a Bicomplex Cousin one family on the minimum domain product domain containing omega. And this theorem says that the Cousin one problem has always positive answer. Okay. So this theorem says that the Cousin one problem has a positive answer. And here we say that this statement, both statements that's in one complex variables in the Bicomplex case are equivalent. Okay, well, let me some comments and let me say some comments in Spanish. Déjenme hacer algunos comentarios. Entonces, como dije, esta teoría de funciones bicomplejo holomorfas o bicomplejo meromorfas resulta exactamente un anfibio, no es una exageración. Como espero haberles podido mostrar, hay resultados que son muy parecidos a una variable compleja. ¿Como cuál? Como los enunciados clásicos de los teoremas de Mittag-Leffler y de Weierstrass, si los ponen en términos, como vienen casi en cualquier libro, si los ponen en términos de funciones meromorfas y cubiertas. Pasa lo mismo en el caso bicomplejo. En el caso bicomplejo, insisto, es un anfibio porque tenemos ceros aislados o ceros no aislados. Tenemos líneas de polos, tenemos singularidades esenciales, ¿ok? Y el concepto de dominio de holomorfía tiene sentido, pero aquí resulta que todo los dominios de holomorfía en el caso bicomplejo son dominios producto y que todo problema inducido problema de Kusan 1 o 2 inducidos en cualquier dominio, cualquier función, para empezar cualquier función holomorfa se extiende al mínimo dominio producto. ¿Ok? Y entonces eso va a repercutir en las soluciones para el caso bicomplejo meromorfo. ¿Sí? Bueno, pues creo que esto era todo lo que les quería. Bueno, esto era bibliografía. Este es ¿cómo se llama? El artículo que les decía yo, que espero que ya salga publicado este fin de año, donde hablamos de la relación entre ser bicomplejo holomorfo y la condición de Stolz. Bueno, pues es todo. Muchas gracias.
We thank Professor Tovar. Any questions or comments? I don't know if Professor Fornes want to participate or what's a mistake with the microphone. No questions? Okay.
Okay.
So, una pregunta tal vez muy simple. Las conjugaciones no dan acciones sobre este espacio de funciones.
¿Sobre qué?
Las conjugaciones que estén dando un grupo por ahí que está actuando sobre este espacio de funciones.
Las conjugaciones dan acciones sobre, bueno, esas conjugaciones para empezar, por ejemplo, las normas, dije que había varias normas. Las normas no son reales, las normas son complejas, ¿sí? Y las conjugaciones dan precisamente acciones sobre el álgebra precisamente de funciones bicomplejas. Eso es lo en general.
Sí. Ok, gracias.
Another question or comment? Ok. Doctor, no sé si continuamos a la 1.
Pues yo creo que está programado a la 1, entonces